You know, this field has seen its fair share of sunrises. We've been producing it for quite a few years now, and throughout most of that time, it's been pretty good to us. But as the old saying goes, all good things must come to an end. This field is no exception.
You see, as an oil and gas reservoir gets older, it usually begins to produce more water. Most of this water can be removed using some type of production separator. However, some well fluids aren't so easily separated. These are known as emulsions and require special processing.
This is the first section of a three-section module on emulsions and electrostatic treater principles. In this section, we will look at emulsions, how they are formed, and several ways that they can be treated.
Treating emulsions is an expensive process, so it's good to know a little about them.
In an emulsion, one liquid is spread out or dispersed throughout another in the form of small droplets. In oil field emulsions, water is usually dispersed in oil and referred to as a water in oil emulsion.
In order to hold these emulsions together, some type of emulsifying agent is needed.
To form an emulsifying agent collects on the surface of water droplets found in the oil. As more of this agent coats the droplet, it forms a tough film, which keeps the water droplets from combining or coalescing.
The most common emulsifying agents found in oil field emulsions are asphalt, resins, paraffins, and oil-soluble organic acids. Different emulsifying agents will occur naturally in different reservoirs. In order to break an emulsion, these emulsifying agents have to be neutralized or destroyed. In the field, an emulsion may be called tight, which means hard to break, or loose, which means easy to break, depending on the type and amount of emulsifying agent present. The stability of an emulsion is dependent on several factors, including the type of emulsifying agent, viscosity of the oil, the API gravity of the oil, water percentage, agitation, droplet size, and age of the emulsion. Now that we've seen how emulsions are formed, let's look at some of the methods used to treat them. Treating emulsions can involve one or more of the following procedures: allowing time for the emulsion to settle, applying heat to speed up separation, injecting chemicals to break the emulsion, using electricity to help coalesce water droplets, or using mechanical devices to remove free water. Let's see how a few of these work. First, we need an emulsion. So we'll use this jar, add some oil, add some water, then we'll shake it real good. We have our emulsion. The simplest way to treat an emulsion is through settling.
Since water is heavier than oil, it will settle to the bottom of a vessel, just as our emulsion is doing here. Now, the time needed to completely separate an emulsion is called settling time. Though some emulsions can be adequately treated with settling, it can be a slow process. So one way to speed up this process is to add heat.
Heating an emulsion aids in several ways. It causes water droplets to move faster and collide more frequently with more force, rupturing the film of the emulsifying agent. This allows heavier droplets to form and settle out. The heat also lowers the viscosity or thickness of the oil, which allows the water droplets to settle out more easily. Heat also speeds up the chemical action by causing water droplets to expand and rupture the film. The droplets can then merge into larger ones and settle out.
When using heat to speed up the separation process, it should be applied only as needed. Now, too much heat will waste energy and cause greater wear on the equipment. Also, excessive heat can cook off the lighter ends of crude oil, resulting in lost revenue. A third method to speed up separation involves adding emulsion-breaking chemicals. These chemicals react with the film around the water droplets. This reaction destroys or neutralizes the film, which allows the droplets to combine and separate from the oil. Just like using heat, chemicals should be used only as needed. Too much chemical is wasteful and could cause an oil and water emulsion to form. Two other separation methods involve mechanical devices and electricity. Mechanical devices, such as gun barrels and free water knockouts, utilize gravity to separate oil and water. Electrostatic treaters use electricity in conjunction with heat and chemicals to separate oil and water. Now, we will discuss electrostatic treaters in sections 2 and 3. Those are the most common methods of emulsion treatment used today. To find out which methods are used in your area, ask your supervisor. Well, it's time to stop the tape and read your student manual. Look at this section of the tape again if necessary, and then answer the questions at the end of section 1. While you do that, I'm going to head over to an electrostatic treater. See you when you're finished. As discussed earlier, the goal of any treater is to break an emulsion so water will settle out, allowing clean oil to be obtained. The selection of a treater depends on such factors as climate, amount and type of well fluids to be handled, characteristics of the emulsion, and the cost of the unit. In this section, we're going to look at the electrostatic treater and its components.
This is the second section of a 3-section module on emulsions and electrostatic treater principles. In this section, we will look at the basic components of an electrostatic treater.
Electrostatic treaters, sometimes known as chemelectric or electrochemical treaters, refer to treaters which use heat, chemicals, and electricity to break an emulsion. The electrostatic field in the treater helps coalesce water droplets so they will settle out of the oil. The electrostatic treater for any lease is designed to handle the well fluids of that lease. Now, because of this, any number of modifications can be made to the basic design. So let's just identify some of the basic components. Located all around the treater, they serve various purposes as the treating process is taking place. Treating an emulsion is really a simple process in concept. Emulsion enters the vessel through this pipe. Once processed, water exits here and here. Gas, which has separated from the emulsion, exits at the top of the vessel. Of course, for all this to happen properly, a number of different components are involved. Two of the most obvious components of emulsion treaters are the stacks and fireboxes. Fireboxes contain gas burners, which provide heat for the treater. Because the firebox generates a good deal of heat, a safety device called a flame arrestor is fitted to the firebox. The arrestor is a series of aluminum vanes placed close together to keep the flame from burning outside the vessel. Another safety device located here is a fuel gas scrubber.
The fuel gas scrubber prevents entrained liquids from going to the burners with the fuel gas. If the scrubber fills with liquid, a float rises and shuts off a valve which stops the gas from flowing to the burners. This prevents the possibility of a fire.
As mentioned before, the produced fluid enters the treater through the inlet line. Now over here, these are the various outlet lines for the treater. This is the free water outlet line with the free water dump valve and the level controller. In the center is the oil outlet line and the oil dump valve. This is the treated water outlet with its dump valve and level controller. Connected to the level controllers are gas air supply lines. These lines supply either gas or compressed air to the level controllers so they can work properly. These are the sight glasses. They help the operator see the water-oil interface levels in the treater. Now, on the bottom of the treater are drains for emptying the vessel for repairs or to remove accumulated solids. Now over here, we find the thermometer, which indicates treating temperature, and the thermostat temperature probe, which maintains the desired treating temperature. Here's the low-level controller, a safety device installed on the treater to ensure that the fire tubes are always covered with liquid. This prevents the fire tubes from overheating. Now, up here on the top of the treater, we find the gas equalizer line. This pipe allows gas pressure to be equalized between the internal sections of the treater. Now, relatively close to that line is a safety relief valve, which relieves excessive pressure in the treater. Sometimes a rupture disc will be used in conjunction with the safety relief valve. On the electrostatic treater, a transformer will be used to step up the incoming voltage to power the electrical grids. Located on the transformer is an indicator light, which burns as long as the grids are working correctly. Connected to the transformer is the voltmeter, which measures the voltage of incoming electricity. And finally, a circuit breaker protects the transformer from power surges. Now that we've seen the exterior components of the treater, let's take a quick look at the interior components. Remember, we'll be looking at these in more detail in the next section. Basically, the interior of an electrostatic treater is divided into three sections: an inlet section, a surge section, and a treating section.
In the inlet section, we find a baffle, downcomer, water wash, flow spreader, fire tubes, and weir. This section provides initial gas and water separation from the emulsion. The surge section, which contains a float and clean oil distribution pipe, keeps the treating section fluid packed or completely full of liquid without any gas remaining on top. In the treating section, we have another flow spreader, electrical grids, and the clean oil collection header. In this section, the final treating and settling take place.
Now you've seen the major external and internal components which make up the electrostatic treater. In our final section, we're going to see how these components work together to treat emulsions. It's time now to read section 2 in your manual. Look at this section of the tape again if necessary. Then answer the questions at the end of section 2. When you finish, we'll look at the operation of the treater in closer detail. In the last section, we saw each of the major components of an electrostatic treater. Now we get a chance to see them all work. We'll follow an emulsion through each section of the treater and see how the treater operates. Finally, we'll look at some symptoms of an improperly functioning treater.
This is the third section of a three-section module on emulsions and electrostatic treater principles. This section covers electrostatic treater operation.
Electrostatic treaters are used for three-phase separation. That is, they separate oil, water, and gas. Like conventional treaters, electrostatic treaters do not receive raw emulsion. Chemicals are normally injected into the emulsion upstream of the treater. So by the time the emulsion reaches the treater, the treating process has already begun. Let's follow an emulsion as it flows through a typical electrostatic treater.
As the emulsion enters the inlet section, it splashes over the downcomer and flows downward to the bottom of the vessel. Free gas is released as the emulsion strikes the downcomer and rises to the top of the inlet section. Most of the free water in the emulsion quickly settles out, and the remaining lighter liquids move upward through the water, which serves as a heated wash. As the emulsion continues to rise, it flows through a spreader, which distributes the emulsion along the length of the fire tubes. As the emulsion moves upward across the fire tubes, several things happen. The fire tubes heat the emulsion, which aids in the separation of oil and water. Heated emulsion rises and spills over a weir out of the inlet section. Water, which has separated from the emulsion, settles to the bottom of the inlet section for removal through the free water outlet. Gas, which has separated from the heated emulsion, rises to the top of the inlet section. A gas equalizer pipe allows gas from both sides of the baffle to be equalized, gathered, and removed from the vessel through the gas outlet. From the inlet section, the emulsion flows to the surge section. The major purpose of the surge section is to keep the treating section fluid packed. Fluid packed is a condition where the vessel is completely full of liquid with no gas on top of the liquid. Finally, the emulsion reaches the treating section. Here, flow spreaders ensure an even distribution of emulsion throughout the treating section. From the spreader, the emulsion rises upward towards the high voltage alternating current electrical grids. Electrostatic treating begins below the lower grid and is completed between the upper and lower grids, where the water droplets combine or coalesce and settle out. As the heated emulsion rises through the electrostatic field, water droplets are given an electrical charge which elongates and polarizes them. The alternating current causes the water droplets to rapidly move around and collide into each other with enough force to break the film surrounding each droplet. The water droplets combine into larger drops and settle to the bottom of the treating section for removal through the treated water outlet. The oil, which has separated from the water, then rises to the top of the treating section. There, a clean oil collection header skims off the clean oil for removal from the treater.
Now that we've seen how the electrostatic treater functions overall, there are some areas that need to be discussed in more detail regarding operation. These are the electrical system, fluid level, operating temperature, and operating pressure. Now, the electrical system of an electrostatic treater consists of two electrical grids and a step-up transformer.
The two grids are suspended one above the other in the treating section. The upper grid is grounded to the vessel shell and is adjustable so the current can be regulated to meet varying requirements. The lower grid is not grounded and receives the output from the transformer. The transformer is the heart of the electrical system. A circuit breaker located between the power source and the transformer protects the transformer from electrical power failures. A fused disconnect at the power source is recommended for maximum safety.
Fluid levels throughout the treater are maintained by dump valves and level controllers.
The oil level in the treating section is maintained by the oil dump valve, which is operated by a float in the surge section. When the emulsion rises above a preset level in the surge section, the float rises with the emulsion and causes the dump valve to open, enabling oil to leave the vessel. When the emulsion returns to the preset level, the dump valve closes and oil accumulates in the treating section. This always keeps the treating section fluid packed.
Free water and treated water levels in the treater are maintained by water dump valves. Like the oil dump valve, water dump valves open to remove water when the interfaces rise above preset levels and close when the interfaces return to the preset levels.
Both water dump valves operate by means of interface level controllers, which use gas or compressed air to open and close the dump valves. The controller opens or closes the valve by diverting gas or compressed air to the diaphragm of the dump valve. The gas or compressed air pressure offsets the spring tension, holding the diaphragm in the closed position. This lifts the diaphragm and water flows through the dump valve. When the interface returns to its preset level, the level controller vents the gas or compressed air, which seats the diaphragm and closes the dump valve.
Operating temperatures are also an important part of the treater operation. The lowest possible temperature to adequately treat the emulsion should be used. The electrostatic treater has an advantage over conventional heater treaters because lower temperatures can be used. Treating temperatures usually range between 85 degrees Fahrenheit and 135 degrees Fahrenheit. The temperature of the emulsion in the inlet section should be kept around 140 degrees Fahrenheit, so the temperature of the fluid in the treating section around the grids never falls below 70 degrees. Should the temperature fall below this level, the grids will not be as effective treating the emulsion.
The relation of chemicals to temperature is another important factor to consider. Usually, less chemical is required to treat a warm emulsion. However, the savings in chemical costs with higher temperatures may be offset by the loss of revenue caused by gravity and volume losses in the oil and increased fuel costs.
Temperature controls, or thermostats, are an important part of any emulsion treater. If they fail to function properly, the burner could remain off or on all the time. If it stays off, the emulsion may cool so it doesn't completely break. And if the burner stays on, the treater may overheat, or the lighter ends of the oil may cook off, resulting in lost revenue. Likewise, fire tubes should be inspected at periodic intervals. Since most emulsions being treated contain a certain amount of sludge and solids, the fire tubes should be checked for corrosion, rust, and any accumulation of scale. Most electrostatic treaters operate under working pressures of 5 to 50 psi. The maximum working pressure for any treater can be found on the manufacturer's information plate attached to the treater.
Oil, water, and gas discharge lines must be equipped with controls, and the treater itself should be equipped with pressure relief devices that have enough capacity to protect the treater if pressure increases.
During operation, the inlet and surge sections are operated at a slightly higher pressure than the treating section. When there's not enough entrained gas in the incoming fluid to maintain pressure, a makeup gas line is usually connected to the gas equalizer.
There are several reasons why higher pressure is maintained in the first two sections. First, the differential pressure assures a positive flow of fluid from the surge section to the treating section. Second, the treating section must be kept fluid packed. Finally, there must be enough differential pressure to move clean oil to the storage tanks.
No matter how carefully you think you've operated your treater, occasional problems will appear. Three of the more common problems are emulsion in the lease tank, free water in the lease tank, and oil in the water disposal system. Emulsion in the lease tank is an indication that the proper chemical heat combination is not being applied. Both the chemical injector and treater should be checked for any necessary corrections. If neither is malfunctioning, the characteristics of the emulsion may have changed and a different chemical may be required. If the water outlet lines are plugged or the water dump valves do not open, free water has nowhere else to go except out the oil outlet into the lease tank. If all valves are operating properly, the treater may not be able to handle the amount of free water produced, and a free water knockout unit should be installed upstream of the treater. Finally, if you're having problems with oil in the water disposal system, this can result if the oil outlet is plugged, or the oil dump valve is stuck closed, or the water dump valves are stuck open. Sometimes when the oil outlet on a treater is below the oil inlet on the lease tank, and the back pressure valve fails to hold a positive pressure on the treater, oil will go through the water outlets into the water disposal system. Well, that ends this section on the operation of electrostatic treaters. In it, we've seen how an electrostatic treater works, some of the more important components, and how they affect operation. And we looked at some of the common problems associated with treater operation. This also ends our module as well. In this module, we've seen what emulsions are and how they're formed, as well as why it's important to break them. And we discussed the components and operation of a typical electrostatic treater. So take some time now to read over this last section in your student manual. Look at this part of the tape again if needed, and then answer the questions at the end of the section. You know, as our fields begin to get older, company revenues are going to rely more heavily on the ability to successfully treat emulsions. So the safe operation and maintenance of the treaters, such as the electrostatic unit we talked about today, is going to become more important in day-to-day production. And the successful operation of that equipment relies on you.